Let's talk about functions and mathematical models. So our objective for this video lecture, we want to build and analyze mathematical models that involve functions. So really what we're doing here, and I kind of just put a double arrow, we're constructing a function. Okay, and the function has the form f of x equals an expression involving x. Constructing a function that is based on the information given and what you know. And then we're going to use that function to ask some questions. Okay, so I'm going to do 3 examples of this, which I think is probably the best way to kind of go through this and kind of talk about what I'm thinking about as we construct these mathematical models. Okay, example 1, we're going to talk about the situation where we are describing the distance from the origin to a point on a graph. Okay, in this case, we have let P equal xy. Let that be a point on the graph y equals x squared minus 1. And the first thing you want to do here is express the distance d from P, from that point to the origin, as a function of x. Okay, so we're trying to construct a function and using the letter x as a function of x. Okay, let's draw a picture of this thing. So I'm not going to get fancy. I'm simply going to draw this graph, y equals x squared minus 1. So here's where I am. This is the xy plane. X squared minus 1, I know, is the parent graph is y equals x squared. Subtracting 1 means I'm going to drop down 1 on the y-axis. And I wind up going through here and here, 1 and 1. And so if I can get this to come out right here. This is the graph. That's pretty close. It's a parabola. This is the graph of y equals x squared minus 1. Okay, and I want to express the distance from a point that's on this graph to the origin. The origin, of course, is here. So let's just put a point on here. Okay, so let's just put a point, and this is my point, and it's the coordinates are x, y for P, and this is the distance d. And I'm going to the origin. So this, of course, is the origin. And the origin, as we know, is at the point 0, 0. Okay, so we want to express this distance from P on the graph of y equals x squared minus 1 to the origin. Okay, well, we need to remember the distance formula. The distance formula, let's recall that. So we got to pull some things in that we know. The distance formula says d is equal to the square root. Okay, I'm using d for distance in this case, of x2 minus x1, the quantity squared, plus y2 minus y1, the quantity squared. Okay, so let's express this as a distance. Okay, so the distance d here, okay, is the square root. Well, here I have an x, so my x, this is my point. I'll do x, I'll go from here to here. So this is going to be x minus 0, the quantity squared, plus y minus 0, the quantity squared. Okay, that's your distance. I'm going to read, I made a mistake here. I'm going to talk about this as the function. The distance, I'll take that back. Never mind, sorry about that. Mistake on my part. So there's my distance. Okay. This is point 1, this is point 2 in my case. So the x coordinate of point 2 minus the x coordinate of point 1, the quantity squared, plus the y coordinate of point 2 minus the y coordinate of point 1, the quantity squared. Now I want this to be I want to express this distance as a function of x. This distance has an x and a y in it, so it is not a function of x. If you'd like, I will simplify this. Okay, so clearly this is not a function of x. But I know what y is. Y is equal to x squared minus 1 up here. So this distance as a function of x is the square root of x squared plus y squared, but y is x squared minus 1, the quantity squared. Okay? Okay, so now I have the distance as a function of x because x is the only variable in this expression. Let's go back up to here when I talked about what our goal was here. Construct a function where the function, in our case d of x down here, but the generalized f of x equals an expression involving x. Okay, well this expression again involves y, but I know what y equals, so I can replace it here, and I can simplify this. X squared minus 1, the quantity squared. Okay, I'm going to rewrite that as a multiplication problem. X squared minus 1 times x squared minus 1. I just rewrote, I expanded this. I got this. Now I'm going to do some math. Come down here. I have x squared. X squared times x squared is x to the 4th. Let's see, minus 2x squared. And then plus 1. So I just multiplied this out using the distributive property. And I can simplify this. And normally you write your highest power first. So x to the 4th is the highest power. I have a positive x squared and a negative 2x squared, so I'm left with a negative 1x squared plus 1. So the distance as a function of x is right here. The distance from the origin as a function of x is the square root of x to the 4th minus x squared plus 1. Okay? So all of that, we drew a diagram. Just a notice, we then remembered that the distance from a point, the distance between 2 points is using the distance formula. One of our points is always, it's on this line, so it's an xy, and the other point is 0, so we're left with this. But that curve is x squared minus 1, so we can rewrite this substituting x squared minus 1 in for y to get a function of x only, do some algebra. And here is our distance formula, our distance function. From any point on the graph, y equals x squared minus 1 to the origin. Okay, letter B. Okay. If x equals, okay, what is d? If x equals 1. Okay. How far is the distance? How far is the distance from here to here if x is 1? Well, x is 1 is right there. How far is that distance to the origin? We can see it's 1. We can also use our formula. The distance when x equals 1 is equal to the square root of 1 to the 4th minus 1 squared plus 1. Well, this is 1 minus 1 plus 1, which equals 1. And we knew that from looking at it, but here's also from our formula. Okay, now let's talk about when is it closest, okay? For what value, whoops, I think I still have space, I'm still okay. For what value of x is the distance closest. Okay, so here's our distance between, obviously the further up we go on the curve, the further away we're getting from 0, the further the longer the distance is. We know that from here to here it's 1. We know from here to here it's 1. The question is it closer in here? When is it the closest? Okay. So when it's the closest, we want to minimize the distance. When is the distance at its minimal, at its smallest? Okay, so what do? Let's graph d of x. This is the distance formula. Let's graph it. Let's graph the distance in this particular case, and let's find the minimum. Okay, so pull up my calculator. I think I'm okay here. I'm graphing this and I want to find the minimum. So let me go to here. Okay, let me clear out what I had in there. Okay, second square root x, whoops, I made a mistake in my writing here. I bet you caught that. This should be x to the 4th minus x squared. Okay, so x to the 4th minus x squared plus 1. Okay, now when I minimize that, I'm going to do my zoom and just take a, let's go to, well, I'll just do a standard. So here's the graph of the distance. Okay, that's the graph of the distance. Now we know what the minimum is. The minimum is a low point in the graph. So let's take a look here. I want to zoom in a little bit here. I know that I'm going to come in between, let's go between -3 and 3 and 0 and 2. So window from -3 to 3 and from 0 to 2. Let's zoom in on that one. Here it comes. So I have 2 minimums in the graph, and that makes sense. Look here, if there's one place on where x is positive, because the graph is symmetrical with respect to the y-axis, there's one place over here as well. Let's find the one that's on the left here of the axis. So second calc, let's calc that minimum. Set our bounds, go to the left side of that minimum, go to the right side of that minimum, and press enter. It looks like when x is -0.7. Okay, so when x is, okay, so 1, I won't put 1, I'll just put a dot there. Okay, when x is -0.7, the distance, d of x, go back to here, the distance is 0.866. I'll call it 0.9. The distance equals 0.9, which is certainly less than 1. Okay, and we can also, let's look at the other side. Okay, we have another one here in our distance where the distance is a minimum. So second calc, let's calculate the other minimum. In this case, I want to be over here. That's my left bound. Here is my right bound, and it looks like it's also, and it makes sense because it's symmetrical, that it's +0.7, and again you get a distance of 0.9. So also, when x is equal to +0.7, the distance is also 0.9 units, and that's the minimum. Okay, so that gives you a sense of, constructing a function. As we used our distance formula, we recognized that this was not a function in x because we have an x and a y. So we substituted to make it a function of x. We simplified. And this is the distance with respect to x of any point on that curve. And we can find any point we want. We found 1, and then we found the minimum by using the calculator. Okay, let's look at 2 more examples. Area of a rectangle is example 2. A rectangle has one corner in quadrant 1 on the graph of y equals 25 minus x squared, another at the origin, a third on the positive y-axis, and a fourth on the positive x-axis. express the area as a function of x. Let's draw a picture. So we're going to keep it simple. Here is my positive x and my positive y. One corner is at the origin, and y equals 25 minus x squared. Well, I know what that does. Okay, what does that do? When x is 0, y is 25, so I'll put 25 here. And this goes from 25 down to 5. Okay? So again, look here. When x is 0, y is 25. When x is 5, 25 minus 5 squared is 25 minus 25 is 0. So there's my graph. And we're going to put a point on the x-axis, a point at the origin, a point on the y-axis, a point on the x-axis, and then one of our points is going to be on that curve. And there's my rectangle right there. Okay? And so as you can see, if I move this point up to here, I get a taller, more narrow rectangle. As I move this point down to here, I get a shorter, longer rectangle. And it kind of becomes square-ish as I have it where it is. It's a little bit squarish. Okay, so what do we know about the area? Well, the area of a rectangle is length times width. If I could spell length, that would help. Okay, well, let's talk about what that is. What's the length and what's the width? Okay. Well, the length, okay, this is the length, and we'll call that x. And what is this? Well, this is y, right? This is y. So let's make my bracket a bit better. This is y, but y is equal to 25 minus x squared. So our area is x times y. Okay, but we want as a function of x, so our area as a function of x is x times y is equal to 25 minus x squared. 25 minus x squared. We can distribute, and the area as a function of x is equal to 25x, 25 times x, minus x cubed. Okay, so there's your area as a function of x. And now we can use this to answer questions. Okay, let's take a look at letter B. Domain. What is the domain of this area? What is the domain? Well, the x's, okay, you could have, let's do it in set notation, all x's such that, well, x can't be 0 because you won't have a rectangle. So x has to be larger than 0. And again, x can't be 5 because then you just have a line. You don't have a rectangle. And x is less than 5. That's our domain. X is between 0 and 5 in set notation. In interval notation, because it's not equal to, it's just less than, we use parentheses. And this is the domain in set notation. Okay, let's graph A of x, the area of x, okay, to find the largest area. Okay, let's find the largest area by graphing A of x. Well, here's A of x right here. I'm going to slide it up a little bit so we can pull my calculator in there. Okay, so here we are. This is A of x. Let's graph that, and we'll choose the maximum, the largest area of our graph. The largest area, so again, let's come on to here. We're looking for maximum area. The largest area is the maximum area. Okay, y equals, that's clear what I had out from before. So in this case, I'm going to graph 25x minus x cubed. And again, I'm going to go back, well, I'm going to go to the, I'm going to zoom to the standard to start there again, just to see where how things work. Huh, that's a little weird. Okay, well, I know I want my x's to be between 0 and 5, because that's my domain. My domain is between 0 and 5. So I'm going to go back and go to my window and go between 0 and 5. And let's see what happens. Okay, well, that's between 0 and 5, but obviously I don't need anything below the x-axis, and it comes down. So I need nothing in the negative y territory, and I need to go much higher in the positive y territory. So back to window, my y can start at 0, and let's max out at, I don't know, let's max out, I'm gonna take a stab at 30. And I'll count by tens, see what that does for me. Oops, I didn't go high enough. Okay, so I can't find my max, it's above my screen. Let's go back to my window, and let's max out at 50. Again, we'll just count it by 10 on the y scale, and let's see if that gives me my maximum. There we go, I got my maximum in there. So the maximum area takes place at the top of the area graph. So let's go calculate a maximum, number 4. Okay, again, I need left bound, right bound. Tell the calculator where to look. Left bound is there, go to the right side of this hump. That's good. Take a guess, press enter. It maxes at 2.886, I'll call it 2.89. Maximum area. Okay, let's go back to here again. The maximum area is 48.11, that's the maximum area, and it takes place at 2.89, when x equals 2.89. Maximum area is 48.11 units, square units, at x equals 2.89. Okay, again, I'll look at my calculator to show you that again. When x is 2.89, I have a maximum, and that maximum is 48.11 right here. It's interesting because this is a quadratic, the x is not at the halfway point. You got to go past the halfway point to 2.9 approximately, and then you go up and draw that, and you're going to come up with the maximum area of this rectangle. Okay, last question. Let's take a look at some uniform motion. Everybody's favorite thing. Uniform motion, constant motion. Distance equals rate times time. Okay, suppose two planes are flying at the same altitude and they're headed toward one another. So we're going to crash. One plane is flying due south. It's flying at 400 miles per hour, and it is 600 miles from the potential intersection point of the planes, from the crash site. The other plane is flying due west, so it's flying this way. It's going west at 250 miles per hour, and it's 400 miles from the crash site, from the potential intersection point. Okay, letter A. Let's build a model that expresses the distance between the planes as a function of the time. Okay, first things first, let's get a picture in here. Okay, so here is going to be north, and here is going to be east. Okay, XY coordinate. One plane is flying due south. Okay, so here's my south flying plane coming this way. Okay, it's coming this way, and it's coming south at 400 miles per hour. And at time 0, it's right here, it's 600 miles. Okay, this is 600 miles. It's heading due south, So it's coming from the north, heading due south, 600 miles away when it starts. It's traveling at 400 miles per hour. Our other plane is going to be here. I have to appreciate my very, very fancy planes. It's traveling west, so it's coming in from the east. It is currently 400 miles. This is 400 miles away at time 0. And it's traveling this way at 250 miles per hour. Okay. We want the distance between them. Okay, well, this is the distance between them. Okay, this is the distance between those planes. Now, obviously, as they get closer, as both planes travel, the distance gets shorter and shorter and shorter until they potentially crash. Okay, the distance between them, as this plane moves west and this plane comes south, they get closer and closer. Okay, so what do I know? Well, I know the distance formula. The distance is equal to the square root of x2 minus x1, the quantity squared, plus y2 minus y1, the quantity squared. We're going to have to use that somehow. Okay, what is that distance? Well, the distance is changing. Okay, now, what is this length? Well, this length turns out, it starts at 400, but every hour it loses 250 miles. Okay, so after 1 hour, it loses 250 miles, after 2 hours, etc. So the distance from here to here is 400 minus 250 times t. Okay, at time 0, the distance is 400. At time 1 hour, the distance is from here to here is 150. Okay? Similarly, with this distance, at time 0, the distance is 600. From here to here is 600. At time 1, it's 200 miles away because it's come in 400 miles after an hour. So this distance is 600 minus 400 times t. Okay? Now remember, distance equals rate times time. Rate, 400 miles, times time, t. So the distance, this is the distance minus the distance, and we can do that. Okay, so our distance at time t is equal to the square root. Okay, well, we're taking wherever we are on this line minus 0. So the x2 is 400 minus 250t minus 0, the quantity squared, plus this length, wherever we are, the point is here, minus the origin. So this is 600 minus 400 times t. Okay, that's the location on the y-axis. Subtract the y-coordinate of the origin squared. Okay, let's make this let's neaten this up. This is going to be 400 minus 250 t, the quantity squared, plus 600 minus 400 t, the quantity squared. Okay, so there's your model. I'm not gonna worry about writing all of that out. That's a good model for us. Okay, we can just use that. Okay, so now let's talk about how close do the planes get to one another. How close do the planes get to one another? Okay, well, close means we're minimizing the distance. Minimize distance. Okay, how close do they get? We're minimizing the distance. So let's put this in our calculator. So we know that our function, d of t, equals the square root of this whole expression. And let's minimize it. Okay, so I'm gonna, let's see, I'll get my calculator in here. I'll slide this up a little bit so that's probably better. And let's minimize this distance. So let's go back to here. Y equals and clear. Okay, second square root. We're gonna do, this first is the parenthesis here. 400 minus 250x, the quantity squared, plus parenthesis 600 minus 400x, close that, the quantity is squared, find my squared key, come out of it. Let's again, I'm going to do a zoom, standard, I like to start there. Let's see what my graph tells me about the distance. I'm not seeing much from 10 to negative 10. Obviously they don't get that close. Okay, let's zoom out. Zoom out. See what happens here. Didn't see anything. Okay, let's try, let's tell you what, let me take a stab at, the distance. This maybe, let's see, my window is, oh, my distance is only going to 40. Okay, let's say, I know my time is positive, so I'll do my time, the x. I'll go for my t is in hours. How about we'll do 2 hours? Because I know, looking here, that at 250 per hour, it's going to go past the origin and past. So I'll go to 3 hours. Let's see, my distance can be huge, but it's going to be 0 higher. Let's go to 1,000. No, they start off at 600. So we'll go to 600, and we'll count by hundreds. Let's see if this does anything for me. There we go. Okay, that worked. Okay, so I see a minimum right here. Let's calculate that minimum. And again, I need left bounds and right bounds. Enter, and it looks like they get, how close do they get? 318 miles apart. If I round this to the nearest whole number, how close do they get? The closest they get is 318, whoops, I put an 80 there. 318 miles. And when does that take place? That takes place after a little over an hour, 1.08 hours. At t equals 1.08 hours. So at 1.08 hours, they get as close as they're going to get. This distance is minimized, and then they pass or they do whatever they do, and they get further and further apart. So there you have it, 3 looks at how to build mathematical models involving functions.